Hi guys. So what we're going to do today is we're going to look at systems again, except this time what's going to be different is that we're going to have some quadratics involved. So we'll look at some intersections with parabolas, and what we'll also do is actually use quadratics in order to be able to solve these. So the first thing we're going to do is just look at some things graphically that can happen here. So one case we'll look at is if you have a line intersecting with a parabola. So if that happens, you could have a case that looks something like this. Well, if that's the case, this could have no solutions. Okay, it's possible for the line to not intersect the parabola. It's also possible for the line to hit the parabola exactly in one spot. If it does that, that's referred to as the tangent line. You may have heard that back in geometry. But what's new with these equations and these systems is it's possible for that line, that parabola, to actually intersect in two places. So it's possible for you now to have two solutions, and that's something you haven't had so far. Up until this point, you really had one solution, infinite solutions, or no solutions. In this case now, we actually could have two distinct solutions. All right, we'll also look at some cases where we have a parabola and another parabola. So if that's the case again, it's possible for them to not intersect at all. It's possible for them to intersect in one spot exactly. And it's possible for them to intersect in two places. Now, one thing you'll see later on in this unit, really at the very, very end, is we'll actually look at some parabola graphs that instead of going up and down, actually go vertical. And if that's the case, if you have a vertical parabola intersecting with a horizontal parabola like that, you could actually even get 3 solutions or 4 solutions. So we're probably not going to see many of those today because we haven't done those sideways parabolas yet, but that is a possibility now that we're introducing some new graphs looking at these intersections. So to start, we're going to go ahead and look at solving these by graphing. So really this is just graphing review, making sure you guys remember how to graph these quadratics. So in order to graph this from standard form, you can do two things. You can do negative b over 2a to get your vertex, or you can rewrite it by completing the square. And I'm going to go ahead and do that just because I think that's good practice. So x squared minus 2x plus blank minus 1 minus blank. Remember, we're doing minus because we're trying to keep this equation balanced, and those blanks are on the same side of the equation. So to find what goes in the blank, take b, divide it by 2, and square it. That gives me a perfect square trinomial. And now it's in vertex form. So my vertex is at 1, negative 2. This graph's going to open up, no stretches, no compression, so it's going to follow that parent function pattern. Right 1, up 1, right 2, up 4, and right 3, up 9. All right, graphing the line negative 2x minus 1, y-intercept of negative 1, slope of 2. Sorry, slope of negative 2. So there's my graph, and you can see this is an example of one of those tangent lines where it only touches that parabola in one spot. So that intersection is my solution, and there's only one. All right, let's look at the next one. We got 2 parabolas. So again, graphing practice here. Vertex of that first one would be 1, 1. It's going to open up. It's been compressed by 1/2. So typically that pattern, but we're going to compress it by half. So right 1 up 1/2, right 2 up 2, and that's really enough for me to get a good picture at this point. All right, second graph, vertex of 1, 1. You're probably going to see the intersection point now. Slope has been stretched by a factor of 2 and reflected. So again, we're multiplying those by negative 2. So there is my second parabola. And again, you can see there is one intersection point here, and that one intersection is at 1, 1. All right, so what we're going to do now is we're going to solve some of these algebraically. So what you'll do, the examples you're going to see are going to be the exact same ones that are on your notes. I think there's one extra, though, that actually isn't on your notes that involves a circle. Don't worry about that one. For the sake of time with recording, I'm actually going to use the ending of the GT video because it has the same examples except for that one additional one. So the rest of these algebraic examples, you'll see it's still part of the same video. The background's going to change color because I'm pulling it from that video. And again, that one extra example you'll have on there, it's good practice and it's good for you guys to be able to see, but again, you won't see that one on your notes. If you don't write it down, it's okay. All right, so what we're going to do now is we're just going to solve these algebraically. And honestly, guys, this is really just more practice on solving quadratics. The biggest thing I will tell you to be cautious about when it comes to solving these, if you use elimination, you need to be careful. What you do not want to do is try to eliminate the x squared term, because when you eliminate a variable, you're trying to eliminate that variable completely. If you eliminate the squared term, you still have an x and a y, and then you're only going to have one equation to be able to solve it, which isn't possible. So if you do elimination, you can only eliminate the variable that does not have a squared variable as well. So in this case, if I want to do elimination for y, that's okay because there are no other y's. What I can't do, though, is say, hey, let me multiply everything by -2, and then I'll eliminate the squared term. That's not going to work because then you're going to have one equation and two variables. So be cautious when using with elimination. I will say I personally feel like on a lot of these, substitution is just an easier process, but that's just me. This first one, though, we'll go ahead and do elimination because, again, if we eliminate y, that's okay because that's all of that variable. That variable is completely eliminated at that point. All right, so that gives me this equation that's left over. That equation is quadratic. It's not going to factor, so we can try completing the square or quadratic formula. And you'll notice inside this square root, that discriminant is going to give you a negative value. If we're giving the square root of negative, that's not going to be any real solutions. And again, because we're talking about this practically, when we talk about systems, we're talking about where they intersect. If I'm getting a negative answer here, it means those two graphs don't intersect. Okay, these are parabolas. This is a case something like this. Okay, or I mean many other options the way it looks, but the point is that those graphs will not intersect. So there's no real solution. You do not need to find imaginary solutions on this, just like you didn't need to when you were doing those inequalities. All right, on this next one, again, either elimination or substitution. I'll go ahead and do substitution because it's set up pretty easily for that. And you'll notice, again, these really aren't that difficult. It's really just extra practice on solving quadratics. Okay, so set that equal to 0. This is going to factor. Only one possible x value, which means there's only going to be, well, sorry, it doesn't necessarily mean that, but we only have one possible x value here. Okay, so I'm going to take that x value, and I'm going to plug that in to either equation. I'll go ahead and do the bottom one because that's a little bit easier. So my solution here is -2, 0. If you wanted to write your answer as x equals -2 and y equals 0 and box that, that's okay. Just be careful you make it clear that which y is associated with which x. Because going further in these, when you have multiple solutions, those x's and y's do need to be paired together in your solution in order to be clear. You can't just say these are the x's and these are the y's. You have to know which x goes with which y. All right, if you're feeling pretty comfortable, pause the video, try these ones on your own. All right, I'm going to go ahead and do substitution. So I'm going to take, this one's already solved for y, so I'm going to plug it in. Now, the reason I did this one in particular is to make sure you guys are careful. When you subtract, you are subtracting that entire function. So this becomes x minus x squared minus x plus 1. So x minus x is going to cancel out. I will go ahead and get negative x squared is equal to -5, which means that x squared is equal to 5, which means that x is equal to plus or minus the square root of 5. So now I have two possible answers for x, positive square root of 5 and negative square root of 5. Each of those x's is going to have a y coordinate associated with it. So I'm going to take that x and I'm going to plug it in to either of those equations. Doesn't matter, it's up to you. I'll go ahead and use the top equation, but I'm going to go ahead and just solve that top equation for what y is to make it a little bit easier. So that top equation, that's x plus 4 is equal to y. All right, which means if x equals square root of 5, the y value that goes with it is the square root of 5 plus 4. Or more frequently, you'll see that written as 4 plus the square root of 5. There's nothing wrong with writing it the other way, but personally I like writing it this way better. That way it's very clear that the 4 is not under the square root and you don't get confused. So that is one solution. Your other solution when x equals -5 then y is going to equal 4 minus the square root of 5. So those are two distinct solutions. You can either write them that way, or you can write them as an ordered pair. It's up to you. But what you can't do is just write, here's all the x's and here's all the y's. You need to make it clear which x goes with which y. All right, on this one, again, I'll do substitution. Take this, I'll plug it in. And really, you just have a big quadratic equation. I'll set it equal to 0. This can factor. I get two possible values for x. And again, remember, each of those x values is going to have its own y value associated with it. So to figure out what that is, plug it into either equation. So y equals, I'll use the bottom one, 2 times 5 squared minus 5 plus 9. That gives me the y coordinate of, let's see, that's 25, 50, 54. So x equals 5, y equals 54 is one solution. All right, the other one, again, plug it in, negative 2. So 2 times negative 2 squared plus 2 plus 9. So that's going to be 4, 8 plus 9 plus 2 is 19. So your other solution is negative 2, 19. So two possible intersections here. All right, just a couple more. Again, very similar type problem. Up to you how you work it out. In this case, you could do elimination because you can eliminate y. Again, we don't want to try to eliminate just the x squared because that's still going to give us a variable and we're not going to be able to solve it that way. But we can go ahead and do 3x squared plus 4x. Those y's cancel out, equals 0. And then hopefully you guys know this is an easy to factor and solve question. This is something you want to factor. Take out that GCF. So your two possible x values are 0 and negative 4/3. Each of those is going to have its own y value associated. So let me just rewrite this. All right, so with x equals 0, I would get y equals 2. With x equals negative 4/3, I would do negative 4/3 squared, square the top and the bottom. That's going to be a negative 16 over 9 plus 2. Get a common denominator, and that's going to end up being 2 over 9. So negative 4/3, 2/9. All right, and then the last one before the word problem. This one is a circle, okay? You know that because you have an x squared and a y squared. And again, we don't need to worry about graphing this. If you want to graph it, you can. Just as a reminder, this would have a center of 0, 0. The radius would be the square root of 10. That's what that graph would look like. But let's just go ahead and solve it algebraically. All right, substitution is going to be easiest and kind of your only option here. Take this y, plug it in. So negative 3x plus 10 squared equals 10. Remember, when you square this, you are not squaring the individual terms. You have to square the entire binomial. Negative 3x plus 10 times negative 3x plus 10 and FOIL it out. So that's going to give you 9x squared minus 60x plus 100. And now just combine like terms. Set it equal to 0. And before I try to factor this, I'm going to reduce it. Okay, this is an equation, so I can divide everything by 10. And now it's pretty easy to factor. Perfect square trinomial. Only one possible answer for x. Take that x value, plug it into one of your equations to get your y value. So your solution here is 3, 1. All right, last one, just a word problem. So just an example of some things that you can do with these systems when you're dealing with some nonlinear stuff. So it says the area of a rectangle is 120 inches squared and the perimeter is 46 inches. We want to find the dimensions, so the length and the width. Okay, so if the area is 120, that means the length times the width is 120. And we're just going to use x and y because we're used to that. If the perimeter is 46, 2x plus 2y is equal to 46. Now this equation actually is not quadratic, but the reason we're including it here is because you're going to need a quadratic equation to solve this. So you can solve for either x or y in this one, kind of up to you. I'll go ahead and just get x by itself. So we'll do substitution. So x is equal to 120 over y, and then I'm going to go ahead and plug that in. So this is 2 times 120 over y plus 2y equals 46. So that's going to give me 240 over y plus 2y equals 46. And although it may not look like it right now, this is a quadratic equation, because what I can do, let's go ahead and multiply everything here by y. That's going to give me 240 plus 2y squared equals 46y. And this is now a quadratic equation. All right, to make it a little bit easier to work with, I'll divide everything by 2. Oops, forgot to divide that by 2. And let me rearrange it. There we go. And this is going to factor. There are numbers that multiply to 120 that add to a negative 23. Those numbers are negative 8 and negative 15. So your possible answers for y are 8 and 15. And then just because both of those numbers multiply to 120, the option for x is the other one. So it's clear here, it doesn't matter which one's length and which one's width, your dimensions are going to be 8 by 15 or 15 by 8. All right, so that's it for systems. Again, not too much new here, really just kind of combining two things we've done so far this year together. And again, you've noticed a pattern here. We're getting extra practice in solving these quadratics. Solving quadratics, guys, it's really important. It's something you got to be able to do pretty quickly and easily. Figuring out, hey, does it factor? If it factors, go ahead and getting that done.